Okay, ladies and gentlemen, it's time to check your answers. The real number system has a classification system basically to tell you what type of numbers are which. So the first things you learned when you were a little kid is how to count, first, second, third. We use these for place values in like track events and things. And you'll notice that it does start with 1, and you can continue counting by ones all the way on up. So these 3 dots mean that it's going to continue forever and ever. And let's see, the next number system is, or the next set of numbers is called whole numbers. So the only difference between whole numbers and the counting numbers is that you now include 0 in the set. So a whole number is considered 0 and then on up with the counting numbers. And then, of course, we learned about integers last fall. You know that if you think about a number line, 0 will be in the middle, your positive numbers to the right, your negative numbers to the left. But notice that the numbers are whole numbers. The definition then that you could use is that whole numbers and their opposites are considered integers. Notice there's no decimals or fractions. So what you have when you start talking about decimals or fractions is the term called rational numbers. Okay, I always like to think that rational kind of rhymes with fractional. So rational, fractional, we have this example, 3/4. Okay, we could turn this into a decimal, 0.75, but I'm going to leave it in fractional form. This decimal here, we could turn it into a fraction, 0.125, I believe is 1/8. So again, I could make the fraction, or I can make the number look like a fraction, and it's considered rational. 0.3 repeating, even though it does go on forever and ever and ever, actually converts into the fraction 1/3. So again, it's fractional, so we know it's rational. 1.1, this could be turned into the fraction 1 and 1/10 if we use our place value. Again, fractional means rational. And then something we have still to talk about is square roots. Okay, when you take the square root of 4, you're looking for the value times itself that gives you 4, and that would equal 2. So here's the thing. Some people forget that even whole numbers can be rational, and here's why. We know the value of the square root of 4 is 2. If you want to make a whole number look like a fraction, remember you can divide any number by 1 and it doesn't change its value. So I was able to record my answers so that it looks like a fraction, and that's how I know it's rational. So here's your definition: any number that can be expressed as a fraction of 2 integers. So again, we can convert all of these into fractions, and that means they are rational. And then if you know anything about this little part that we add to the word rational, okay, IR is the prefix. What it means is that we cannot turn the number into a fraction of 2 integers. Okay, so again, these two groups of numbers are kind of opposites of each other. You know from working with pi that the value is approximately 3.14, but it's not exactly 3.14 because the value of pi actually never ends. So when you have a decimal value that never ends, but also doesn't repeat in a predictable pattern, you cannot turn this into a fraction. So that's why we call it irrational. Square root of 2, if we do that calculation real quick, this is what your calculator spits out. We get approximately, remember this is not an exact value because your calculator cannot possibly calculate all the way out to infinity. Alright, but as you can see, the decimal digits do not repeat. There's no fancy pattern, and again, it's going to go on forever and ever and ever because we cannot turn this number into a fraction. So that's why we call it irrational. Now guys, all of these things are parts of the real number system. So think of classification in science class where you might take a living thing and break it up. Is it a plant? Is it an animal? Each animal is then broken down into further groups. All right, I don't remember the exact classification system that we use, something about kingdom, phylum, class, genus, species, something like that, okay? But you've been familiar with it in science class, so imagine that the number system, that's just how we break it down, okay? They're all real numbers, okay? But whether they can be turned into a fraction or not, that's the first classification we look at. Okay, if we can turn it into a fraction, then we then look closer inside these and say, hey, some of them could be integers. And by the way, rational numbers can be negative. So I could turn this into a negative, or I could turn this into a negative. So you're still allowed positives or negatives, whether you're rational or irrational. But under integers, remember, it has to be whole numbers, okay? We don't have any decimals or fractions under integers, and we certainly don't have any of those under whole numbers. Remember, we don't even include negatives with our whole numbers. And then, of course, back to the beginning when we talked about counting numbers. When you count seats or something, or people in the room, we would start counting with number 1, number 2, and each person gets counted. All right, so that's just kind of a way to remember all the different types of numbers that we have in our system for math to classify numbers. What you're doing with this information now, if I can get to that page, is this right here. Okay, this is called a Venn diagram. And a Venn diagram sometimes includes information like we just talked about. And what it does is it helps you visually see what's going on. So first thing I want you to notice is this big box. This is holding all the real numbers that we could possibly come up with. And by the way, there are numbers called imaginary numbers. They would not be in this set. Imaginary numbers would be like over here in La La Land. Okay, you'll learn about imaginary numbers when you get to high school. And they're used for different things, okay? So we focus at this level on real numbers, okay? Within the real numbers, we do have 2 separate classifications. Remember, irrational numbers can't be made into a fraction. And then here's the other dedication, which is rational numbers, okay? So you're either going to fit your numbers into one of these 2 categories, but within rational numbers, you can kind of see how we break it down even farther. Okay, if we don't have any fractions or decimals, but we still have positive or negative whole numbers, we would be an integer. And then remember, if you don't have any negatives, you would be a whole number. And then if you don't even include 0, you would have your smallest set, which, by the way, still goes on infinitely, right? Your natural or counting numbers, you could count infinitely. And that would include the set called a natural number. So really, this assignment, I wanted you to familiarize yourself with the diagram. And then what you're supposed to do is you're supposed to take your numbers, okay? 2 times the square root of 64. Square root of 64 is 8. So basically 2 times 8 is 16. 16 is one of our counting numbers, okay? So even though it seems kind of tricky, it really does represent a value that you could use to count. So that would go in this box. Negative 15. Remember, integers are the values that have negative values and they're whole numbers. So we would put negative 15 with our integers. This, when you reduce it, 16 divided by 4 is 4. So that's another counting number, or natural number we call it. I'm going to write that this way so it fits better. And then we need to type in the square root of 75. So 75 has a value that is approximately, this goes all the way across your screen, so bear with me. It's got 8.66, 025, 4038. So that is an approximate value. It does not end. It does not have any good repeating values. So that means this is an irrational number, and it would fit over here in the diagram. 0 we said is a whole number, so we'd squeeze that in right here. And I guess my computer's locked up for a second. And then finally, we'll let this thing catch up to us. Finally, we have the decimal, negative 12.2. So remember, if we can turn negative 12.2 into a fraction, then we can call it rational. So remember, you can use second PRB, and it does turn it into 12 1/5. So again, this is rational. We can make a fraction out of it, so negative 12.2 would go down here in your diagram. So again, it's just another way to look at the definitions that we learned and place the numbers in the appropriate places. Again, keeping track of who's rational, anything that can be made a fraction, and who's irrational, something I couldn't ever turn into a fraction. I mean, if you do this on your calculator and hit second PRB, it's not going to change into a fraction for you. So that brings you to, I believe, this page. This page in the notes has some examples. Again, it's reviewing the definition. If something's rational, you can convert it to a fraction. If something like pi goes on forever and ever, we can never turn it into a fraction, so that's why we call it irrational. And there's a couple examples down here showing you again that you can convert them into fractions simply by putting a 1 under a whole number. Repeating decimals can be turned into fractions, so all these are rational examples. And then over here, again, pi is irrational because you can't write it as a fraction. And then the square root of 2, if we look that up, square root of 2 has a value that goes on forever and ever. And let's see, we wrote this down earlier, 1.4142135562. And again, it does not have any repeating parts, so it cannot be written as a fraction. So again, down here, I wanted you to go through all these examples, and I think I have it started on this slide for us. Yeah, so 2 squared is 4. I can put a 1 under it to make it look like a fraction. So again, fractional means it's rational. This is already a fraction, but if you wanted to turn it into a decimal, you could. It doesn't need to be, but again, fractional means rational. This one, again, we could convert it if you wanted to, but we don't need to because it's already fractional, which means it's rational. And then 1.765, if you take a second and convert it, I believe you get 153 over 200. And once again, because we could turn it into a fraction, it is rational. Now, this number line down here, what they wanted you to do is they wanted you to take the value, like 2 squared equals 4, and place it on the number line and label it. So 2 squared has the same value as 4. 2/5 has the same value of 0.4. So to me, it kind of helped to turn it into a decimal so I could guess best where it's going to fit on the number line. And then -1.5, you know, is going to be right down the middle. And 1.765 is going to be a little bit closer to 2. So I'm going to write it here, and you might start running out of room, so feel free to kind of write it sideways. Alright, so checking the ones in the middle. So far they've all been rational. This one is still rational. Another rational because it does repeat. Finally, we get something that's irrational. Okay, pi is allowed to be negative, so that would turn out to be about -3.14, but it does not continue in a repeating pattern, so that's why it's irrational. And then the square root of 49 is actually 7, so that one is rational also. And then let's see, negative square root of 6 goes on forever and ever, so it's irrational. 2 times the value of pi is about 6.28, so again, pi is in there, so it's irrational. And then this one you actually can convert to a fraction, so remember, fractional means rational. Alright, so there's all those answers again, and if you look carefully at your number line down here, you'll see how all the values were placed. A couple of them you kind of have to guess. Remember, it's about 6.28 for 2 pi, so again, that one's going to go there. Some of them are going to be exact. Remember, square root of 49 was exactly 7, so you want to make sure that's on your number line properly. And if you're comfortable with all your answers and you've made corrections as needed, remember to please tape in your tab divider for this unit first, and then today's notes on the first page over. See me with any questions.